Ladies and gentlemen, welcome to the talk at the Milliways stage about how to use AI in penetration testing. Jacob and Richard are going to tell you all about this interesting topic.
Thank you. Good morning and welcome to our presentation. We're mastering the maze. There is like a small company icon in some of the corners. We got like a training deal, so please don't mind that. Yeah, let's first talk about motivation and our agenda. So how did we came up with this topic? Both Richard and I wanted to learn a bit about AI, and security is a nice topic, so we thought about like combining those two. And yeah, what did we want to do? We wanted a bit learning by doing and tried to create a neural network that could find an optimal action in a pen testing environment. Yeah, so today in this talk you will hear me talking a bit about deep Q learning, how it works, and yeah, how the best solution is found, and then Richard will explain how this deep Q network can be used in penetration testing. So first we started using some tutorials, and there are actually a lot of tutorials for deep Q agents that are related to gaming. So we had a look at these, and yeah, started with some of the tutorials, and yeah, these. Sorry. So the game tutorials kind of make sense because in the video game you have like a state, and there are a few actions you can take, but there are a lot of states, and these actions and states, we will have a look at them later, are perfect for Q learning or deep Q learning. So, we also try to make an own agent for a maze, and the title is from that, but that went okay. So how does Q learning actually work? So I already mentioned states, and there are some elements that are required for Q learning. First we have an environment. The environment is like the thing the agent interacts with. So that can be a game, and agent can interact with that. Or the environment is like a real-world environment, and that's also possible. In this environment, the agent has some actions. That's like the steps it can perform. So, for example, in the example game environment, Mario can jump or go right, go left. That are possible actions. And it's like the things you have on the controller, the buttons you can press. That's like the actions the agent can do. There also is the agent itself. It's represented as Mario here, but the agent is like all of the things combined, kind of, because it's like the main part of the AI. One of the most important things is the reward. So there is like the score in the upper left corner of the environment. That's not really the reward, but that's what you might associate with the reward. Also maybe the time. Both of the things are in the dotted boxes. But the actual reward we are aiming for are the game failed or the game won state, kind of. So if the level is completed, then there's a big positive reward, And if the level is failed, there is a huge negative reward to influence training. And also the kind of most important element in the learning algorithm is the state. That is some kind of representation of the environment, and the state is kind of what the agent sees. It can be, for example, the position of an object or its velocity or things like that. So in Q-learning, we have some tables. These tables have a state and actions associated. And for every state action pair, there is a Q value. And the Q value inside the table is the expected reward over the time. So if I have a state X and I look in the table, and if I go right now, then I expect the reward in the end to be 1. And if I go left, then I expect the reward to be -10 or something like that. The rewards over the time, so looking into the future, kind of the rewards always are a bit discounted, so the reward in the action itself is a bit higher than future rewards. And also using Q-learning table, you can, if it's fully trained, it kind of memorize the perfect way, and you can find a perfect path. But that's quite problematic if you have like a lot of states or infinite states. So therefore, we used a deep Q-learning network. It's a neural net, and as first layer, you input state parameters. It's not like the state itself, but for example, a position and velocity and things like that. So you input a state, and after some hidden layer magic, then an action falls out. So instead of memorizing the table, the nodes in the neural network use an approximated optimal Q value, and therefore find like the perfect action if there are a lot of different states, and then there can be infinite states instead of a list that is in the table like before. I hope you understand the basic concept of Q-learning, and Richard will now show what you can do with that.
Thank you, Jacob. So to use this kind of algorithm for our real-world example, we have an agent, this handy person sitting in the middle, and the goal is to have a network of systems, so the landscape of all the systems with vulnerabilities accounted to one of them, or even more than one. And the goal is to find the optimal path through the network. So to attack the first system, gain access to the second, which vulnerabilities get the highest reward, which are most prominent to attack. So instead of the game example we heard earlier, we want to train an algorithm that decides on the given network, which is the optimal path, the optimal attack path through the network, and what actions to take to gain the highest rewards. Therefore, we have some systems with low-hanging fruits, for example, so very easy to exploit vulnerabilities, or very hard to exploit vulnerabilities. So the low-hanging fruits would be optimal to attack first, gain access to the system, or some systems have higher rewards because some critical data is accounted to it, more traffic runs through the system or something like that. So there could be many parameters to account for this. And the agent itself knows in the beginning a list of systems in our case. So we have a list with, for example, 100 systems, And then the algorithm would go and find vulnerabilities at the beginning system. It searches, is it worth to attack a found vulnerability? Is it giving us a reward that is acceptable for the algorithm? If, for example, an SSH service is configured in a way that it's easy to exploit, this would give us access to the system, maybe root access, so it will generate a higher reward. And the algorithm decides to use an attack vector, or it has the option to select a new system, do some reconnaissance states, and find new vulnerabilities on the new selected system, and then jump from system to system, deciding is it worth to attack a vulnerability on the system, or even more than one, or is it worth to go to the next system. So in order to have it do that, we give the reward explained depending on how great of an impact the vulnerability is, but we also give a penalty for action taken. So we don't want to create a lot of noise, scan all the system at once, and so on. So, for example, the selecting of a new target would be a penalty to encourage the algorithm to do some exploitation of the vulnerability bounds on the servers. And depending on what reward will we get back from each action, we have the landscape, and in the best case, algorithm that decides go to system A, then go to system C, attack there, and have at the end a big path through the network that we can use afterwards to do our exploitation. So the goal of this algorithm is not to exploit the vulnerability itself, but is to decide if it's worth to exploit it or not. So the final exploitation and more in-depth research would still be done by a pen tester, or maybe in some stage or another to the algorithm itself, but we come to that later. In this research we done for this presentation, we have set up a small project with a very simple environment and a very simple landscape to train the DeepQ network. You can see we got a result of -29, so we averaged more penalties than we got results back. At first sight, when we compare it to the stochastic optimal result, it's not the best score you would hope for. So at first sight, our algorithm may not have taken the best route through the network, and we could explain this by the very few data points we've given and the very rudimental network we set up. So to answer the questions we come into with this talk, is it possible to master the maze, to find the way through our system landscape with the DeepQ learning algorithm? First of all, as we've seen in the last slide, there are some problems. For the algorithm to work properly, we need more diverse and also more data overall to train the algorithm, and it's not very easy to obtain for a wide variety of systems to train the algorithm. And without this data, it is also possible to say that the DeepQ learning algorithm is maybe not the best way to achieve this goal. So you need a lot of extensive knowledge about the server, about the vulnerabilities to train the algorithm. But if you have enough data, if you have enough knowledge, the outlook for this algorithm is that it can produce a sophisticated attack vector on our system landscape, and it's very useful if you have a very large system landscape, very complex system landscape, maybe one with that grown over time. Nobody knows exactly what is running where, what is going on in the network, and you can use it to do automated pen testing stages in this landscape use the data recovered by the algorithm to do further investigation, or even, as said, train or extend the algorithm to do the actual exploit in the steps where we have the attack vector. And then it could be generating automated results of the network. We can use it to harden our network without the need of extensive human resource for, as said, very large networks. So to summarize it, the lessons we've learned. So our goal was to know something about the deep Q network, deep Q learning, and use it in pen testing. We have achieved that. We have gained a lot of knowledge about both of this, and we have a good understanding of how to develop it further to be useful in our showcased example.
Thank you for your interesting talk. We still have time for a few questions. Anyone wants to ask a question? We have a microphone over here. Please go to the microphone to ask your question. Signal Angel, does the internet have a question? The internet does not have a question yet. They're still asleep. But we have one in the audience.
How does this compare to things like Ponagotchi?
Sorry, I haven't.
Ponagotchi, which is used for Wi-Fi attacks and uses an actor-critic model.
Yeah, so our goal was, first of all, to gain knowledge, and in this case, it is possible to design the algorithm for your own use case. So to provide it for the network you have and optimize it.
In terms of the exploits, does it basically check service version and then has some local database with exploits, or can we also hope for misconfigurations or keys in bash history or something like that?
Yeah, so in the current state, it does not use very sophisticated databases and everything. But our goal is to extend it to have a more advanced data set, the algorithm used to evaluate what vulnerability is useful or not. And then the more data it has to evaluate all those things, the more the higher impact the result is of the systems, what is vulnerable, what is not, and what could be exploited or not.
So how is the training of the neural network actually done? Because we don't have a direct feedback what action will result in the desired state or final state. So how do you train it supervised?
So in the training we used like kind of a test environment. So we did not really had good data because we realized that companies are not so willing to share kind of network scans and things like that. So we had kind of a not really mock, but quite mock environment. So there was not really a good I'm not quite sure how I phrase it. So they're kind of like we kind of use a mock environment. So we gave the answer if it's vulnerable or not a vulnerable service.
And that rounds up our talks. Please give another round of applause to Jacob and Richard. Thank you for your talk.